Good evening, everyone. Happy Thanksgiving, whether or not you celebrate it or not. I'm just so glad to be here to see this community, to see so many people. Today, I'm going to present how Foursquare uses its owned and operated apps to drive quality and accuracy in movement data, how we discriminate real from fake data, which is a huge problem to this industry, and how we use the data to train algorithms for stop detection and value attachment. Uh, all of these components that I just mentioned, they power the Foursquare movement engine that generates the so-called daily diaries of millions of people every day, from billions of GPS signals around the world. So here is the outline of this presentation. I'm going to talk about the who's, why, what, and then the conclusion. So I'm going to start by talking about who is Foursquare, what do we do? And then I'm going to use some example to show why are the owned and operated apps important to us? Why is it a differentiator for Foursquare? And then some more examples to show what our methodology does to take advantage of these data that we own. So what is Foursquare? I think this animation shows a lot of information about what we do in Foursquare. I mean, to summarize, we translate raw signals. It could be raw GPS pings or raw POI information from the websites into meaningful data about places and the movement between them. In other words, if you look at this animation, we're trying to reconstruct a user diary about how this user moves from places to places in their real life. So as Ilya just mentioned, Foursquare was founded in 2009 as a consumer app company. So, over the years, we have made a few transitions to a different company now. But still, one of the most important ingredients of Foursquare is the consumer apps. We have the Swarm app, which is a checking app where you can use it to record where you go to do this so-called live logging. And the Foursquare City Guide is a location discovery and recommendation app where it's kind of like Yelp, where you can search for places you want to go and it'll give you some recommendations. We also have a movement SDK, formerly known as Pilgrim SDK, for third-party app developers. So if you want to create your own app and you want to integrate some of the location technology from Foursquare, you can use this movement SDK. Because we have done everything for you. Over the years, we have become more of a data and technology company. So two of the most important data sets we own are the places and the movement data. So I'm going to focus on talking about the movement data today because this is what I work on most of the time. But to summarize, movement is basically a multi-sensor stop detection technology that has 9 billion visits per month as input from 500 million users across the world. And places are just a bunch of machine learning and artificial intelligence models to maintain the data on more than 100 million venues in the world. We use a lot of different resources coming from both the user-generated data in our apps and also third-party information that we scrape from the internet. And what we really want to go from now is to become a platform company in the location industry, where we can provide a unified tool and platform to serve a lot of different customers in different use cases, like marketers, if they want to run, measurement and ad targeting, or enterprise users who care more about the business intelligence and insights, like higher level information about their business. And also we have Studio, which is a visualization and analytics tool that helps third-party developers to visualize their data on the map view. So it would be something like this one here. Location industry is hard. We have a lot of challenges in this industry. For example, the input data, the GPS ping signals that we collect from both first-party and third-party devices is very noisy. So I think what makes this industry unique is that if you compare it to a lot of the other machine learning fields like image recognition or natural language processing, their input data is very well defined. Like, for example, when you see a picture, it's basically a bunch of pixels with RGB values, right? When you see a text, there might be typos and everything, but when you see a letter A, it's a letter A. But in location data, a lot of the GPS signals are actually very noisy. It contains a lot of errors, especially in like highly populated urban areas where there are a lot of tall buildings to block the GPS signal. So you could have, 100 meters of error from where you really are to what the signal tells us, right? So, and also a lot of the third-party providers we purchase data from, they contain a lot of fake or artificial data. And we need to be able to filter them out. A third challenge is how to acquire this so-called ground truth data. For example, a lot of businesses, they have their own like transaction data, right? How many credit card transactions happened on this day for this store. That data is very valuable. It's what we consider the ground truth, real data. But it's also very hard to purchase these data. And even if you did, it's also very hard to normalize it to match our visitation data, because there's a lot of biases for different business. Like, for example, if I go to the demographic distribution for people who go to I want to use not a political correct example, but let's say a men's warehouse place is going to have a very different demographic to people who go to, say, a women's fashion boutique place, right? So it's a problem how we normalize, how we counter that bias in their data as well. The last but not the least challenge we have is how to evaluate our model. Let's say we have the algorithm, we have the models, and we think they're good, but how do we objectively say they are good? In the location industry, unlike a lot of the industries I just mentioned, like image processing or NLP, there just isn't a good open source data set for evaluation. So we have to come up with our own evaluation data set for that. I mean, that's what makes Foursquare different, is because we have the owned and operated apps. I'm probably gonna skip all these, marketing materials here. But I just want to mention that, first of all, we only collect user-consented data. So we only use data that is given permission by the users. And we have a very high coverage globally, meaning we don't just collect the US data. And we have the best quality data in this industry in terms of, because the data comes from the user input directly. It's our users who tell us the address of this place. It's our users who tell us which place they went to. So on the right side, you can see an example, a screenshot of our Swarm app, which is our check-in app. You can see basically this user has created these check-in history to different places with their timestamp and the venue name on it. So that is very valuable data to us. So then how do we make use of the data, right? Our methodology. Here's a very simplified data flow for our visitation or movement pipeline. We start from these third-party GPS pins. We convert them into raw user visitation data, and then we normalize them based on some aggregated weights to match the ground truth data that reflects the real distribution of the real world. So for each of these three steps, our owned and operated first-party data comes in very handy to help us to do for example, a good data evaluation of the third-party data. Are they good? Are they bad? Should we, just drop this provider because they just give us all fake data? When we generate the visitation data, we have our proprietary snap to place algorithm to try to attach places, these venues, to a user stop when we detect a stop that has happened. And that algorithm takes advantage of our user check-in data as well. So I'm gonna start by talking about the first step here. So here is an example on how we use the first-party data to do a provider quality evaluation. Basically, we ask ourselves how far away, when we look at a 3P device and its GPS signal, how far is it away from what the first-party apps tells us about the same device, right? So we define some labels such as good stop versus bad stop. And for devices overlapping in time, we look at the distance between the 1P and the 3P stop. If the distance is within 250 meters, meaning what the third-party data tells us is close enough to what the first-party data tells us, then we define that stop as a good stop, and vice versa. So on the right side, you can see that it's a bar chart representing different provider quality. I mean, I hid the provider names so that I don't want to make them look embarrassing, but you can clearly see that basically the higher this darker bar is, the higher the quality is from this provider. And this dotted line represents the volume, the number of GPS pins this provider sent us. You can see clearly that between this red provider and this green provider, they have similar volume. As a matter of fact, they are two of the biggest providers, third-party providers for us. But one has almost everything bad, versus the other one has a vast majority of the stops we label as good. So when next time we want to talk about dropping a provider, which one to drop, right? It's the red one. And furthermore, we can also train a machine learning model to check the veracity score for each provider based on this data. But none of this could be done without owning some high accuracy, high quality first-party data from our own and operated apps. Here's another example about providers. So once in a while, we want to add a new provider, right? uh, before we start paying them money for ingesting their data, we need to evaluate how good they are. So, we do the evaluation based on some criteria, like these ones. So on the right side, you can see a side-to-side comparison of basically two heat maps of Manhattan, New York, based on the visit count grouped by H3 hexagon partition of the geospace. So H3 is basically a way to partition our space into smaller areas. Level 9 H3 represents somewhat of I guess like a block-sized area. You can see that on the right side, our first-party visit show a very high volume, at Midtown Manhattan, which makes sense, and some other, distributions, as you can see from this map. On the left side is this new provider. Generally, it shows less volume than our first-party data, but you can see that the distribution is, about the same. Like, it also has the highest density at the same location on this map. So that's good for us. After we do the third-party provider assessment, now it's time to turn these raw signals into actual visits. So what is a visit then? In a mathematical form, a visit is basically a venue with the highest probability given a stop. It's basically when our stop detection algorithm detects there is a stop that happened somewhere at this time. What are the odds that venue A is the actual venue where the stop happens versus venue B, C, D in this neighborhood, right? This is what we call snap to place algorithm. So it connects both the movement data and the places data on both sides. So we use a lot of different features to train the model, but I can categorize them into three major categories. Proximity model basically tells us how far away is this phone from this venue, represented by the historical check-ins to this venue. There's the popularity feature, which represents how many people have checked into this place in the past 6 months, right? So there are just some venues that are always more popular than the others. And then there's the personalized feature, which is based on your personal checking history. So here's a more concrete example of what we consider visits. Basically, you can consider them as mini-me's or copies of historical check-ins. So on this map here, you have three venues. So this pink represents the location of the stop. And around the stop, there are three major venues: Chipotle, which is a fast food place; Gap, and Whole Foods, which is a grocery store. And we look at some of the nearest check-ins that happened to these three different places, and we notice that actually 6 out of the 10 nearest check-ins belong to, say, Chipotle. 2 of them to Gap, and the rest of them to Whole Foods. So we know that probably we have a higher chance of this stop happening inside a Chipotle store than the others, right? But that is a very simplified version of our model. Our actual model is a non-parametric model for learning a venue's spatial presence, and that makes very little assumption about the data itself. But there's also challenges for this methodology. We just don't have enough check-ins sometimes for some venues, right? And also there is biases of data based on the demographics biases in our first-party users, and also when when the place structure becomes complicated, like if you're in a mall, which contains hundreds of different smaller venues. Which should you snap this visit to this mall, or should you snap it to a specific venue that is very close to other venues, right? But nevertheless, let me show you the power of check-ins by a map, because a map is worth a million words. Here is Central Park, Manhattan, represented by check-ins. So different color basically represent a different venue based on their probability of check-ins. You can see that here at the bottom left corner, this green bulb here is actually the sheep meadow, which is just like a grass field inside the Central Park. And you can see that based on the check-ins, we can draw a approximate shape of this sheep meadow without knowing the actual shape of this geolocation itself. And I think it resembles the actual shape pretty well. So basically, in other words, this is to try to reconstruct the place shapes by using check-ins instead of using other methodologies, such as sometimes people draw polygons to represent different shapes. Sometimes people use just a drawn shape, like hand-drawn shape, to represent venues. But in reality, we know that some of these venues, actually the boundary extends beyond the physical shape of the place, right? So based on check-in, this actually probably represents the reality better. Here's another example. So on the right side, you see this, I don't know if you could see it, you see this small red dot inside of this, a small blue blob inside this red blob here. So the red actually represents the Metropolitan Museum itself. But the small blue thing that is wrapped by this red structure is actually a different venue called Metropolitan Museum Steps. Why do we have a separate venue for Metropolitan Museum Steps? I have no idea, but if you're a Gossip Girl fan, you should know it. I'm just gonna put it there like that. But so this example basically tells us the resolution, the high resolution, the high level of accuracy of our check-ins, that where we can even draw the shape of very small arbitrary venues based on check-ins. So once we create the raw visits, a lot of the times we need to aggregate them to generate these so-called normalized visits. Here's an example how we can do that and why we need that. So on the right side, when you look at this blue line, this blue line represents the raw aggregated visits for a specific chain in the last 3 months. You can see a huge drop, huge cliff here in the middle of October last year. We don't know what happened. Nobody told us why they're suddenly sending us less data. Right? But according to our research, usually the missing data comes from either the decrease of total number of devices, so our panel size, or the average visit per user, or VPU for these devices. So in other words, based on the data they send us, these same devices suddenly behave very differently. They become less active. That's why we need to normalize our daily raw visit data to our stable first-party data so that we can correct for this loss of volume. A lot of other people, they have other alternatives because they don't have the first-party data. Sometimes they use the census data to try to compensate for the loss of device count. But the problem with that method is that census data is a very static data. You probably run census like every 5 or 10 years. So it's way behind the actual real world trends. And also the resolution is pretty low. Like you cannot actually do it on a device level. You can only do it on a, say, a zip code level. So on the right side, when you look at this orange line, the orange line actually represents this corrected or normalized visit based on this normalization methodology. And now it looks much closer to this green line, which represents the so-called ground truth data, much better. Of course, it's not perfect. As you can see, towards the end of this curve, there's like an upward trend here. I mean, that's why we're continuously working on improving our normalization methodology here. To conclude, I think nothing said this better than a famous quote in our industry by Alan Kay. He said, people who are really serious about software should make their own hardware. But I just changed software to data and hardware to apps, and I think it still stands. If you're really serious about data and data quality, you should make your own apps. And thank you. That's it.